Mr. Harris with way more hair than he wants to have. But we can't, in this difficult time, we can't worry about that. It's just a bit of hair. I'll be honest with you, I've been losing my hair for so many years that having a little bit more is actually quite pleasant. So, enough about hair. We're today going to be talking about investigative maths. It is something that really excites me, as you can probably tell, because I'm like, oh, excited. We're going to be talking about what real maths is, because this is going to be controversial, and I don't care. Real maths is not what we do every day. Real maths, and we will discover that through the course of the next 20-25 minutes, is what we're going to be doing. We're going to be talking about what real maths is and how it's different from everyday maths. So, let's get started. So why do I keep talking about real maths versus not real maths? You're going to find that out today. I'm going to explain. I'm not just being at all dismissive of the maths we do every day and all the lessons I've been doing. It's important and it's what we study at school. But we don't have the opportunity to do some what I call real maths, because real maths is investigative. It has no answers. There's no finish to real maths. There's no point at which you go, right, I'm done. I've done all of it. I've finished it. You can't finish an investigation. We're going to learn a bit about that more. But first, let's do a starter activity. Here it is. Oh, that's not this. This is just reminding you to send me the work that you're doing. And I want to see pictures of you investigating. This is a brick. What mathematical questions could you ask about this object? You have 45 seconds. Write them in the chat or write them down on paper. Off you go while I say good morning to... Wow, lots of people. Good morning to Eddie and Amber. Good morning to Vera. Good morning, Alicia. Good morning, JJ Games, who I believe has been playing lots of Lego this morning. Oh, no, Eddie's been playing the Lego Legacy. Try and remember to do some maths as well, Eddie. Good morning, Nina. Good morning to the Sharpies who are here. Good morning, Roshan. Good morning, Harry Sharp. Maybe not related to the Sharpies, maybe also part of the Sharpies. Good morning to... well, someone's been retracted. I don't know whether what that was for, but good morning to Kim and Hillard. Good morning to anyone else I missed. Lars is here as well. Right. What questions have we come up with? Is this a 3D shape or a 2D shape? That's valid. What's the weight of the brick? Good morning. Yeah, you're absolutely right. You did answer the game was good. I'm not having a go at you. You're welcome to discuss the Lego Legacy games. I'm just saying that I want to encourage everyone. Good morning, Claire Blaze, William and Claire. How many vertices does it have? Yeah, we talked about faces and vertices and vertices and edges in one of my foundation lessons a few weeks back. What's the weight? We could also talk about what the dimensions are. How many of these you would need to build a wall, to build a house, how much they weigh, how much the house would therefore weigh. All sorts of things. Could you draw a plan of this? And side elevation. What's the density of the brick? There are all sorts of questions you can ask. And the reason I'm doing this as a starter is today, that's the sort of person you need to be. You need to be prepared to ask lots of questions. If you're going to investigate things, you've got to be prepared to ask questions. So, what is it all about? Now, I've talked about this being real maths. In investigative maths, you're given a problem and you explore it. But you don't solve it. You don't fix it. Because you then explore it more. And you then explore it. And you explore it more. And it's exploratory. The easiest way to show you this is with a question. So that's what I'm going to do. You buy a new hoodie. There you can see, if you were in my primary lesson, you'll already see this hoodie because I've been so interested in it, I'm considering buying it myself. You buy a new hoodie, there's a 20% sales tax, but you get a 30% discount. Which would you prefer to be applied first? Would you prefer to have the tax added first or the discount added first? I would like you to put in the chat or just write down what you think your first the first reaction of whether you think it is better to have the tax first or the discount first. Who thinks that? So Harry Sharp's going for the tax first. Okay. Anyone else got any ideas? Nina both wants them both at the same time. I'm not sure how I would do both at the same time, but sure, because you still have to do one then the other. You still need to put them in some sort of order. So you're going with tax, Nina. Good. So we've got tax for Harry, tax for Nina, tax first for Alicia, tax first for Nathan, discount first for Peyton. Hello, Peyton. I didn't say that you'd arrived. Nice to see you. Any others? Okay. So, in order to discuss this, we need to head over to my whiteboard. Here it is, and here I am. So we have a hoodie. In order to investigate, we need to start off doing something called specializing. Specializing is where we choose some numbers to make the problem more meaningful. I'm not the best at drawing hoodies, but here we go. We'll do it something like that. There it is. And it's got a spider in the middle. Now, the price tag wasn't in the question, and this is often true in investigative learning. It had no price tag. Specialising is where we invent a price. Now, I like to use £100. I know that's a lot of money for this, but it makes more sense when we're going to do the thing. So, we're going to first of all do tax first, and then discount second. And on this one, we're going to do discount first, and tax second. So, the tax first. The tax, I believe, in the question said it was a 20% tax, because that's like VAT, and the discount was 30% discount first. So, tax first. 20% of 100, and the reason I've chosen £100, it makes these percentage questions easy, is 120. And then 30% discount, 10% of 120 is 12, so 30% is 36. 120 minus 36 is need to borrow. That's going to become a 1, then a 10. That's going to become 11. That's going to become a 4. That will become an 84. And it's £84. We'll use a different colour to show the other one. 30% discount first. So 100 minus £30, because remember that £100 makes it easy percentages, is 70. But now we're going to do 10% tax. 10% of 70 is 7. So 20% is 14. So we add it on. 70 plus 14 equals 84. Now, who is surprised to see that? Eddie, stop writing JJ so many times. Spamming. Who is surprised to see that they're the same? Anyone? I was the first time I saw this problem. I was like, what? It's the same. In fact, it doesn't matter. But we don't know that it doesn't matter for all examples, because the problem with specialising is we've only done one example. Maybe that's only true for £100. And when you're investigating, you can't tell any facts from one example. You cannot prove it's not a proof. It is not an answer. You can't prove facts from one example. You can have an opinion, but it's not sensible to do so. So what we need to do is go back through the question and see what happens if we change this from 100 to a different price. Because if we change it from 100 to a different price, we have so far only discovered that when it's £100 it doesn't matter. We have not found out that it doesn't matter ever. We have only found out that it doesn't matter when it's £100. So the next thing to do is try specialising for a different example. We're going to try £50. So 20% tax first. 10% is 5. So 20% is 10. Add it on. So we've now got £60. 30% discount. 10% is 6. 30% is 18. Take it away. 60 minus 18 is £42. We're now going to do this one over here, but it's now £50. 10% is 5, so 30% is 15, and 50 minus 15 is 35. 10% of 35 is 3.5, so 20% is 7. 35 plus the tax is 42. It is again the same price. And Nina's still saying, but in real life you get the discount before the tax. Hopefully this should be showing you, Nina, it really doesn't matter. It doesn't matter at all. The 60 here comes, that's an excellent question, Savannah. 60 comes because we had £50 and we've got 10% is 5, 20% is 10, so I've added 50 plus 10. So I've added the tax. You add tax and you take off discounts. This should be showing us that it's suggesting it doesn't matter whether you do the tax or the discount first. It really doesn't matter. But again, this is not a proof. All we've done is 2 examples. It might make you confident in saying, oh yeah, no, I think I know. But mathematically, I would say we've proved nothing. All we've proved is that for £100 and for £50 it's the same. But the whole point of maths is that when you're investigating, you only know if you do specialising and you do one specific example, you only find one specific answer. If you find 2 examples, you find 2 answers. But we want to then do the next part of investigative work. In investigative work, we have specialising, we also have generalising. You buy a pair of jeans and there is a sales tax, but you get a discount. So you get a something sales tax and a something discount. We haven't in any way said yet whether it is only true because it was 20% and 30%. So we've proved nothing. Generalising is where we try and look at the picture, but with if it was not just specific examples. This was specialising because we chose numbers and did an example. And this is how you start an investigation. You choose numbers and do some examples. This is entirely random. You choose random numbers and you choose the random numbers to allow you to get some examples of the problem. But this does not constitute an answer. You can't come back and say, I've proved that it's always the same. You haven't. Or we haven't. All we've shown is that for £50 and for £100 and 20% and 30%, then they're the same. That's a very specialised example. So we need to take it forwards. We need to look at jeans. Now this will involve some tomfoolery. It does require us to understand a little bit. Now those jeans are amazing, I think you'll agree. Not quite sure why, but apparently my jeans is now a face. I've made some sort of face out of my jeans. They stand together, that would be a mouth. My jeans, they are going to cost X pounds. Huh? It's not complicated, Alja. Nothing scary here. They're going to cost X pounds. And I'm going to have a tax of Y% and a discount of Z%. Now, I've talked to people briefly before. The reason I put a line in my Z is because otherwise they took like 2s. If you look at that, they're my 2 and my Z, they look very, very similar. Whereas if I put a line in the middle of my Z, it doesn't look like a 2 anymore. Now, one thing, I'm not going to spend too long on this. This is just an explanation. When you do a tax, you do 100 minus Y and that will give you a multiplier. Something like 0.82 would be a discount of 18%. So it's 100 minus y is how you, and then you divide it all by 100. But we can simplify that. Let's say instead of that, these are decimals already. So both the tax and the discount are the decimals that we're using as a multiplier. So for example, the y% could just be 0.82. And the discount, tax would be more. I do apologise, that's a terrible example. Discounts would be that would be 0.82. Tax could be 1.2. This is a 21% tax, 1.21. So tax goes up, discounts go down. Now I've done lessons on percentage multipliers, so you can go back and look at these. The point I'm trying to make is, if I do the tax first, x times 1.21, and then I times it by 0.82, I actually end up with, there's my calculator, I should have opened it beforehand. Next. No, I don't want to activate it. No, back. I want to continue with my current free version, please. I want to do 1.21 times 0.82 is 0.9922. 0.9922 x. This way round, x times 0.82, if I do this one first, times 1.21 is also 0.9922 x. You will notice they are the same. We have only proved it though for a tax of 21% and a discount of 18%. But look at what happens now. X times y times z is xyz, and x times z times y is also xyz. They are the same. We have now, after all the things I've said, it is now proven. We have proven that it's always going to be the same. Because only when you start to generalise, and generalise is where you use like a bit of algebra, or you use letters to stand for numbers, or you try and make it so it stands for things. JJ, you've got to say what you don't get. You can't just say, I want to understand. Nathan, excellent question. If these are not proof, would anything be proof when investigating maths? Yes. Proof comes when you can prove that it's true for all examples. And what this does here, by using the x and y and z, we've proved that it works for all examples. Whereas the others were only proof of 2 examples. This is now a proof for all examples. The whole point of these things is, Savannah, we don't need to be here saying whether we like algebra or not. It's irrelevant. I'm just trying to teach the lesson in terms of investigating. This is special. This is generalizing. This is taking the problem and going, well, what about if I use general ideas? So the only reason we use letters here is, well, this is for any price, for any tax, and for any discount. Whereas this one above here, so the one I'm highlighting now, is a special example, specializing, because I've used specific numbers. Whereas this one here is a generalized example because there's no numbers. I've used letters to stand for different things. Okay? So what we're trying to do is show that it's true for all things. All I've done is shown you one investigation so far. The whole point of investigative learning, we're only at the start of it. You should get stuck when you're investigating, because part of investigating is the process of stuck and aha. Stuck leads to aha moments. Stuck is where you go, I'm not sure what's going on. What? I'm confused. I don't understand. You have to write down, when you're stuck, write down questions about what you're stuck on. Aha is those moments where you get yourself unstuck. Or maybe you speak to Mr. Harris and he explains it and you're like, oh, that feeling of, oh, I get it. Oh, this makes way more sense. It's normal to have lots of stuck aha moments when you're investigating. I do. Let's go back a second and go and look at another question. Sorry, just my mouse was playing up for a second. Here we go. Here's another question. A palindrome is a word or number that reads the same forwards and backwards. It has been claimed that a 4-digit palindrome, that all 4-digit palindromes are in the 11 times table. Are they? Now that picture shows you lots of different palindromes of words. We're talking about 4-digit number palindromes. Let's think about what I've taught you. So we are talking about palindromes, and all divide by 11 is the question. Now, what I've tried to teach you today is specializing before generalizing. I get confused with the spelling of these because I think one has a Z and one has an S. I think it might be specializing has a Z. Specializing means we choose a palindrome. 2, 3, 3, 2. There we go. There's a specialized example. Example 1, we'll call it. That's what you'd be expected to do if you're doing this. I haven't taken you over here. Now you can see it. Palindromes all divide by 11. Okay. So we've got specializing. Sorry, JJ Games asking us. I don't get X times Y. Okay, the reason it's X times Y, JJ, is because I'll go back to that in a second. We'll look at this first, and then I'll go back to that in a second. 2, 3, 3, 2. Does it divide by 11? We're doing a specialized example here. So we're going to do 11 into 2, 3, 3, 2. 11 into 22 go 2 times. Carry the 1 forwards. 11 into 13 goes 1 time. Carry the 2 forwards. 11 into 22 goes 2. It does. Is equal to 212 times 11. So that one works. Have we proved this? No. Not proof. But we always do several specializings first. 3 or 4. So EG2, I don't know if I'm about to be on top of my picture. I'm sure you'll tell me if I am. Choose a different palindrome. 7997. So we're going to do 7997. Divide by 11. Is none. 7. 79 is 7. 29 is 2. 77 is 7. It works. 727 times 11. Again, not a proof. It's only showing that it does work for the 2 that I've randomly chosen. And we can do that with another example. You can keep doing examples. The whole point of this is you keep doing examples. And then, after you've investigated by specializing, you generalize. Now, this is the bit that people might find a bit harder. I'm going to try and explain it as best I can. But before I do, let me just go back and explain to JJ what we were talking about here. He doesn't understand the X, Y, and Z. Well, tax is a multiplier. Yes, we did an example which was 1.21, but we could have just used Y for any decimal. Because it can be any decimal could be a tax. And any decimal could be the discount. We used 0.382, but we could just call it Z. Letters are used to stand when it could be any number. So if it was Y, as it could be any number, then it's X times Y times Z is X, Y, Z. That's how we write it. And X times Z times Y is also written as X, Y, Z. When you times a number together, you get a number times a number. But when you've chosen a letter, the reason we choose a letter is to stand for any possible number. It could be not 1.6, it could be 1.2, it could be 1.9, we could have any number for that tax. Hopefully that makes a bit more sense. Feel free to go back over and watch it later as well. Now, for us to understand this, all 4-digit numbers are the thousands, a hundreds, a tens, and a units. So the number, for example, 2332 is actually 2,332. 232. Hopefully you all understand. This is 2000s, 300s, and 30 and 2. Therefore, remember how I like to use letters to stand for numbers I don't know. What if we called our number x, y, y, x? That would actually wouldn't work algebraically. I can't call that. That's not right because I'd have to times them all together. In order to make it work as a number, I would need to write this as 1000x plus 100y plus 10y plus 1x. 1000 thousands, so x thousands, y hundreds, y tens, and x units. But when we did simplifying expressions, we said, well, we've got 1000 x's and another x. That's 1001 x's and 110 y's. And here's the bit where generalizing helps us to prove. We're about to do a proof because it works for general rules. We can, if there's a number that comes out of here, we can factorize it. I believe 10y is 10 times 11 is 110. I also believe 1001 divided by 11 is 009, and we carry 1001. Are you sure, Mr. Harris? You may have messed this up. Pass 10 on 99, pass 1 on 91. There we go. It's 91x plus 10y with an 11 on the outside. This 11 on the outside means that 11 will always divide by any number. If the number is x, y, y, x, we can divide it by 11. We have proved that it always divides by 11. We started the problem by specializing. We did some examples. We then used some algebra or symbols or anything we need to do to see how we got those. Okay. And we carried that on. Okay. So we've got 11 always divide into those numbers. But we have not finished. Because the final thing I want to make clear to you, the last step, which we're going to talk about in the next time I do an investigation lesson, which will probably be either next Tuesday or the Tuesday after, the next thing you do is extend. We only looked at 4-digit palindromes. Is there a rule for 5 digits? Don't know if this is going to be on me. What about 3 digits? What about 6 digits? We haven't investigated any of those. We've only looked at 4 digits. And the whole point of investigating mathematically is we don't finish. We don't stop. We don't go, oh yeah, I've got an answer now. Once we've got a proof, we go, well, is this always true? We've shown that it always works for 4-digit palindromes. Does it work for 5-digit palindromes? What about 6-digit palindromes? What about 2 digits? We never even looked at 2 digits. Well, in fact, we do already know 2-digit palindromes. Because one of the first things you learnt in primary school was your 11 times table. 11, 22, 33, 44, 55, 60. This is working, isn't it? So 2 digits we can say works because we know our 11 times table, so we know them all. But we could break down this generalizing a bit further and just prove that it works, the 11 times table, because I know some people are struggling with the generalizing. Let's write the 11 times table. Any number that say is AA could be written as 10 A's plus an A. Yes? So if it was 22, 10 times 2 plus a 2. But that is 11A. So of course it divides by 11. Because it's 11A. We've just proven that it must work for all 2 digits. And we earlier proved 4 digits. So this is the point of the extending we go, well, we know it for this. Well, what about this? When we're looking at our original questions, the question is only a starting point, because realistically, this is not a question provided for you by a teacher. This is provided for you by the world. This is a sort of question that someone might be just looking at. They might notice, oh, wait a minute, I wrote down 4224 and it divides by 11. I wonder if it... I wonder. That is what we're really looking for. That feeling of, I wonder. I wonder if... Now, I have got for you some questions which have been in the description below, and they all involve do some specialising, do some generalising, then see if you can come up with it. Have a look at them. I can discuss these further, but I don't really want to until you've had a chance to go and have a look at things. If you're doing one of these and you get a bit stuck, feel free to write questions below this video. Feel free to say, oh, I was doing the question about this and I'm a bit confused, I'm a bit stuck. That's fine. But the whole point of this investigating mathematically, these do not get finished. Because if you said, yeah, I finished it, I saw how Mr. Harris was right in the first one, I saw he was right, and it was like, okay, so what about if it had 100 squares? Oh, and then, yeah, I did that one. Okay, what about if they were if the board was made out of triangles? Oh. And this is the point. We can't finish these problems, but you can take them as far as you want to. Now, there's 3 things that I'm going to talk about in a future lesson that make investigating easier. Diagrams, tables, and writing down your thoughts. Consider trying that while you're doing these investigations. I'd love to see some people's attempts at one of these investigations. See what you come up with. I will... share with you in future how I went about it, and you can see one of my investigations. But that is enough about investigating for today. I hope you've learned something today. I hope that you have enjoyed what I've been covering. I hope it's made sense. Feel free to watch it again if it didn't. If it does get confusing, it's supposed to be from year 5 all the way up to year 9, but it might become confusing for some year 5s and 6s. I get that. That's fine. I'll try and make sure that it's accessible for everyone. But I wanted to make sure that this idea of investigating was... We got started on this idea of do some examples first. So the first thing I would do, if you choose the chess problem, is I would draw a 2x2 square and find out how many squares there are in that, and then maybe a 3x3, and then a 4x4, and start looking for patterns. Looking for patterns is what was all about. Savannah, I had no idea about the gender of my baby, but I'm off for a few days now to try and hopefully my wife will be giving birth, and hopefully next time I speak to you, you will all be able to see a little picture. Thank you so much for joining me. You've got a Taskmaster challenge, you've got a Corbett Maths challenge for today, you've got an investigation challenge, lots of things for you to do today. Hopefully I inspire you to go and give it a go and send some photos in. If not, then enjoy your Lego Legacy or whatever else you're doing for the day. I've been Mr. Harris, you haven't. Take care.